The shift register, which allows the parallel type of input and produces, there are two types of counters, that is the asynchronous counter and the synchronous counter. There are four types of shift register. One is the serial in and serial out register. So they are elementary in design and also less expensive. This ripple counter is an asynchronous counter which are, and again in the serial manner, Q1 will be acting as an input to the D0. Hello students, welcome to the next session of digital electronics. Okay, let's start this session with one of the sequential circuit which is known as the counters. Okay, so the counters, why do we use, what are the use of it and other things about the counters, let's check in this session. Okay. So counter is a sequential circuit which goes through a prescribed states when there is a change in the electric pulse is called as the counter. There are two types of counters based on the flip-flops, various flip-flops that are connected in synchronous or asynchronous manner. There are two types of counters, that is the asynchronous counter and the synchronous counter. Let's look at one of the counter, that is the ripple counter. Okay, so a counter we usually used to count the number of clock pulses. How much time the electric pulse is going to off state and on state. So that will be counted, which is called as the electric pulse. This change in the electric pulse will be counted by a counter which can be applied with the help of the flip-flop. Okay, so it can also be used for frequency divider, that is in a physics related field, to check the frequency of an electronic device. Time measurement, how much time has been used, like in washing machines or in microwave ovens, like that. Frequency measurements, measuring the frequency. Distance measurement, how much it has covered in an electronic device, and also for generating the square wave maps, that is the electric pulses like this. So you can use the counters for this. In this, we use various flip-flops that are used in asynchronous counters and are supplied with different clock signals. Clock values will be changing in a counter. There may be a delay in producing the output because of this change in the state of the electric pulse. There are also a few number of logic gates that are needed to design the asynchronous counters which are not in sync, that are called as the asynchronous counter. So they are elementary in design and also less expensive. This ripple counter is an asynchronous counter which are less expensive when compared to the synchronous type of counter. Here we have a 3-bit ripple counter. Okay, so a 3-bit ripple counter can use the JK flip-flop. Okay, let's what about the flip-flops, types of flip-flops? We can know it in the next session. So we have the JK flip-flop. It uses the high value which is provided to the third counter. Okay, these are the counters. Each counter will have a provision of clock pulse. Okay, will have inputs J and K and produces the output Q and Q dash. Okay, Q0 will be the state coming from the previous. As we know, usually the sequential circuit usually use the value from the previous input. So we can use the Q and the Q dash as an output which takes the state from the Q0. The high value is provided with all the counters to make a change in the electric pulse. So it will be always be low, usually be low. To get it to the high, you have to provide a high value to the counter. To any counter, to make a pulse high, you have to provide a high voltage to the counters. Here we have the clock pulse. Based on the change of the clock pulse, the input for J and K will vary with each electric pulse. Okay, this is the diagrammatic representation of the 3-bit ripple counter. 3-bit is, we have 3 counters. Each counter will accept 1 input. So it is called as the 3-bit ripple counter. Okay, you can have more number of ripple counters, 4-bit, 5-bit. Usually it will be 6 bits, 3 bits, 9 bits, or like that counters you can use. The counter state will be like this. So you have 0, 1, 2, 3, 4, 5, 6 and 7. 7 through 7 states there will be high and low of the electric pulse in the counter. Here we have the outputs Q2, Q1 and Q0. Okay, in this we have the values zeros. Okay, so 0, 0, 1, with each change in the counter state, one of the output will be taken. Since it has 3 bits, 3 bits mean 2 to the power of 3 outputs. Okay, so 8 outputs will be considered as same. It is shown 0, 0, 0 if it is counter state is set to 1. If counter state is set to 0, that is 1, 0, it will be 0, 0, 1. That is this will have the input 0, this will have the input 0 and this will have the input 1. If it is 2, it will have 0, 1, 0. So there are 8 combinations or 8 combinational inputs that you can use in a 3-bit ripple counter. Okay. Along with that, the 3-bit ripple counter used in the behind circuit, previous circuit, has 8 different states from 0 to 7. Each one of which represents a count value. Each represents a count value in the ripple counter. Okay. So similarly, a counter having n number of flip-flops, if it has n number of flip-flops, can have maximum of 2 to the power of n states. So, okay, if you have n flip-flops in a counter, it can have maximum of 2 to the power of n states. Okay, the number of states that a counter owns, how many states a counter can own, is known as its mod number or modulo number. Hence, a 3-bit counter is a mod 8 counter. Okay, so it is a mod 8 counter. What it will do is, a mod n counter may also be described as divided by n counter. So, we'll reduce using the modulus operation. Number of states will be divided by n number of counters. Okay. Why you need this kind of calculation, modulus operation is, this is because the most significant flip-flop that we use, the farthest flip-flop from the original clock pulse, which is far away from the original clock pulse, produces 1 pulse for every n pulses. When comes to the last counter, the electricity will be in lower pulse. So it produces only 1 pulse for every n number of pulse. The last counter produces only 1 output for every n pulses. One pulse for every n pulse at the clock input of the significant flip-flop. Okay. The 1 triggers by the clock pulse. Whenever there is a 0, 0 will be changing to 1 with a set of a clock pulse. So, the above counter is an example of a divide by 4 counter. You are going to divide it by 4 pulses. That means you have 3 plus 1, that is 4 counter values will be used in 3-bit ripple counter. Okay. Then we have the timing diagram using the JK flip-flop in the ripple counter. Okay. We have the timing diagram. How does the pulse changes? Let us assume that the clock is negative edge triggered. Negative edge is in the lower state. Okay. So above counter will act as an up counter. It increases the pulse rate, or it takes the pulse to the positive or high rate. So it is called as the up counter. Okay, because the clock is negative edge triggered. You have a clock which is negative edge triggered. It is lower state. It is in the lower state. So it will be triggered to rise to the high value. And output is taken from the Q. The previous value is going to be provided, which is used to trigger the clock pulse. Okay, here we have the clock with each low and high electric pulse. How does the output changes in the outputs is output value, or the pulse changes in output value is Q0. The pulse will be like this. It is 1 pulse for 1 edges. This one is the edge, changing the state from high to low or low to high or high to low. Each is called an edge. So these are called as the edges. We can call it as the edges. Each edge will have 1 clock pulse when there is a nearer counter. Nearer counters will use or will generate 1 pulse for each clock pulse, 1 low and high cycle. So this is an cycle starting from low, getting to the high and getting back to the low. It is like a cycle. For each cycle of the clock pulse, the nearest counter will produce 1 pulse, whereas the Q1 produces same pulse, the low pulse, for 2 cycles. You can observe that the electric pulse is becoming consistent. That is, 0 is maintained for 2 cycles. 1 is maintained for 2 cycles. So there is no abrupt changes in the states in the counter Q1. Then we have the Q2, which is the farthest from the original clock pulse. Now what happens? We use 4 cycles, which is set as low. Then 4 cycle uses 1, and again 4 cycles low, like that. As the clock pulse, as the counters move farthest from the original clock pulse generator, the state will continue as it is. So its consistency will be maintained. So clock pulse will not frequently change in case of the farthest counters. Okay. So this is the clock pulse that uses the JK flip-flop. Okay. Then we have the synchronous binary up counter. We had the asynchronous binary up counter. Now we have the synchronous binary up counter. An n-bit synchronous, you have n number of bits. Synchronous binary up counter consists of n T flip-flops, n number of T flip-flops. That means the synchronous counters always uses the T type of flip-flop. It counts from 0 to 2 to the power of n minus 1. That much flip-flops will be used. The block diagram of a 3-bit synchronous binary up counter, that is from low to high the pulse will be increased, is as shown in this diagram. Okay, we have the T flip-flops which uses 1 input, 2 inputs, whereas 1 input is a clock pulse and another one it takes the form of a T. It is called as the T flip-flop, and takes the one output Q0, which acts as an input for the next flip-flop, next T flip-flop. This uses each time one clock pulse and one input. You can have 2 to the power of n minus 1 number of flip-flops. Okay, if you have the n T flip-flops, it counts from 0 to 2 to the power of n minus 1 connections. So this is the counter, synchronous binary up counter, which has a counter and outputs are taking from each of the flip-flop in the counter. The next thing you need to know is the shift registers. Okay, so shift registers are the register which shift the value or which shift the bit to the left or to the right. Okay, we have the registers. Registers are the temporary memory cells or storage locations that can be used to store the data temporarily, not permanently. Registers are always the memory locations which are used to store the temporary data. Okay, so in this we have one type of register, that is the shift registers. Okay, what is the use of shift registers? Why do we need these shift registers? Okay, why it is called as shift register is, if the register is capable of shifting the bits either towards the right hand side or towards the left hand side, to any one of the side, it is going to shift the bits, okay, to either left or to the right, which the register which shifts the bit or which changes the position of the bit are considered as the shift register. Okay, so shift registers are used most widely for different electronic devices to quickly change the values. Okay, when you have a digital watch, you have to change the minute counter, second counter. You have to change the second counter for every second, isn't it? You have to shift the values, right? If it is 1, you have to change it to 2, 2 to 3, 3 to 4. How does it happen? By shifting the bits, you will get the new values. New generates the new values, which is used in the electronic devices. So, it is using the shift register. There are 4 types of shift register. One is the serial in and serial out register. Then we have serial in parallel type of shift register. Then we have the parallel in and serial out shift register. And last thing is parallel in and parallel out shift registers. Okay. Now let's take each one of it. Okay. The first thing is the serial in, serial out shift register. So what we can do in serial in, serial out shift register? The shift register which allows serial input, serial kind of input, and produces serial kind of output. Like if you have 110, it is shifted as say 011. It is shifted to the right. It is serially getting the output. If the shift register which allows the serial input and produces the serial output is known as the serial in, serial out shift register. In which manner it is inserted or inputted into the register, in the same way the output will be taken from the register. Okay. The block diagram of the 3-bit shift in, serial out shift register is as shown in the figure. You can observe here we have used one of the flip-flop. Sequential circuits most widely uses one kind of flip-flop for its use. You can combine the flip-flops with the various gates. The thing is, each is using a D flip-flop. It takes the input in a serial manner. So D2 is the input. We have a clock pulse. Okay. So each flip-flop is getting one input from D2 as in the serial manner and produces an output Q2. It is using 3-bit shift register. Q2 will be acting as the output from the first flip-flop, will be acting as an input for the next one or the second one. Okay. Then we have again the clock pulse, which triggers the pulse in the D flip-flop. Now we have the input D1, which is getting the output Q1, and again in the serial manner, Q1 will be acting as an input to the D0. Here we have again the clock pulse given to the flip-flop. It produces serial kind of input. When there is a serial input and serial output which shifts the register to the next flip-flop, it is called as the serial in, serial out shift register. Alright. The next category is the serial in and parallel out shift register. In this, the shift register which allows the serial input, serial kind of input will be there and produces the parallel output is known as the serial in, parallel out or SIPO, serial in, PO, parallel out, serial in, parallel out shift register. Okay. The block diagram of again a 3-bit serial in, parallel out shift register is as shown in the diagram. We have the serial input and a clock pulse. Now, this flip-flop, first flip-flop will produce an output Q2. Q2 is acting as an input to the next flip-flop. Along with that, this input is considered as one of the output. Okay. So, this input acts as an output as well. Input to the next flip-flop as well as output which is parallelly produced. Each flip-flop parallelly produces a separate output and acts as an input for the next flip-flop also. So, the output is acting in two ways in a serial in, parallel out shift register. So, we have this parallel output, then we have D1 acting as which is inputted for the second flip-flop. It produces an output Q1. This input is taken as a parallel output along with the Q2 and Q1 again acts as the D0 input to the third flip-flop and it produces an output Q0. Now we have 3 parallel outputs, that is Q0, Q0, Q1 and Q2. So it uses 3 different bits or it produces 3 different parallel output bits. This is called as the serial in, parallel out shift register. Okay. Next is the parallel in, serial out. The reverse is parallel in, serial out shift register. In this, the shift register which allows the parallel type of input and produces a serial kind of output is known as the parallel in, serial out shift register. Alright. The block diagram of again a 3-bit parallel in, serial out shift register is as it is shown in the diagram. Here we have parallel kinds of inputs to 3 AND gates. We are using AND gates because you cannot directly put the values to all the flip-flops. Each flip-flop must take the input from the previous one. So to get a parallel input, we are using the AND gates here. Okay, it uses the AND gate. These AND gates are connected by an electric pulse with a preset. The values are preset and provided with parallel input. Okay, so why you need two inputs is the AND gate usually uses two inputs. Is a minimum of two inputs, isn't it? So it uses a preset enabled value along with the parallel input. It uses three parallel AND gates to provide one of the input to the flip-flop. One AND gate provides the input to one flip-flop, second one to the second FF or flip-flop, and third to the third flip-flop. Okay. Now, along with the value from the AND gate, we are also getting the input from the another input way. Okay, we are getting two inputs and a clock pulse again for the D flip-flop. It produces Q2. Now, Q2 is acting as an input for the next flip-flop. It gets two inputs in the D flip-flop from D1 and from another AND gate. It produces another bit. The third AND gate is there which produces or which takes the input, one of the input from the previous flip-flop and one from the AND gate, and it produces only one output. There are no multiple outputs. Only one output is produced in a parallel in serial out shift register. Okay, this is one of the kind of shift register. The last category is the parallel in and parallel out shift register. In this shift register, which allows the parallel input, parallelly you can input as well as you can produce a parallel output. It is known as the parallel in, parallel out shift register. Okay, the block diagram of a 3-bit parallel in, parallel out shift register is as we can view in the diagram. Here we have the parallel input. Same as using the AND gate, each flip-flop get two inputs from D2 and the previous preset enabled value and a clock pulse to trigger the flip-flop. So flip-flop needs a trigger. So trigger will be obtained by the clock pulse. Okay, the output from one flip-flop will act as an input for the second serial flip-flop. Along with this input, it takes the output parallelly. Now we have the output Q2. Then this flip-flop also produces an output Q1, which acts as an output as well as input to the third flip-flop. So this is the third one, which produces the output Q0. So parallelly we get Q0, Q1 and Q2, three parallel outputs from three parallel inputs. Okay, so this is the parallel in, parallel out shift register. These are the four types of shift registers that you can use in case of the digital devices. Then what is the use of shift register? So these shift registers are usually used in calculators or digital devices which continuously changes the value. Like you'll be having a console in a washing machine which shows you the timing the machine is running. So that time has to be continuously changing. How it changes is, it shifts the bits to get the new value. If it is 8, 0, 1, 0, so it may shift to get 0, 0, 1 or 1, 0, 0. Like in the gray code, to change one bit in such a coding representation, we usually make use of the shift registers to make the temporary changes in the values. They are not permanent, isn't it? They are temporary. For changing in the temporary values, we make use of the shift registers. Okay. Thank you.